Right, now that we've seen a few more families of functions, we've seen logs, we've seen exponentials, we've seen how to differentiate the trig functions as well. That opens up a lot more sorts of questions. Remember, the key for calculus is solving problems that involves rates of change. I mean, that's what the derivative measures, the rate of change. So, as a recap, any time you have a rate of change, you can express it as a derivative. Now, sometimes you need to build that rate of change using more than one rate. That basically uses, now call it what you like, implicit differentiation, the chain rule. It goes by many names, but it is the same idea. I mean, if you want to find dy to t, you could find dy dx and multiply it by dy to t, dx to t. Because rates are fractions. And so you could think of it like saying, well, the change in x cancels and I get the change in y with respect to t. So let's look at an example. A spherical balloon, and it's being deflated so that the radius decreases at a constant rate. So imagine in your head you've got a balloon and it's deflating. But the radius, when you deflate a balloon, if you think about it, it's the radius that goes down by a constant amount. It's the volume, the rate of change changes, and you can tell that by the noise. If you think of a balloon going down, it goes, and it's like really quick at the end. Okay, so the rate of change of the volume changes as the radius changes. So we want to know what that change of volume is going to be when the radius is 100 millimeters, so 10 centimeters. What's that about that? So what do we know? Well, it's the v to t that we want to find. What can we work out? What have we been given? We've been given the rate of change of the radius. It's decreasing, so we know it's a negative. So negative 10. So I want the v to t. I've got dr to t. If I can work out dv dr, then we've got it. We should be able to work out the problem. So we need something that links volume and radius, and fortunately we have a formula that links volume and radius, the good old 4/3 pi r cubed. So differentiate volume with respect to r, and we get 4 pi r squared. What's significant about that? 4 pi r squared is surface area. Always amazes me, that one. Then the rate of change of the volume is in fact the surface area. Okay, so sub in what we know. dr to t is negative 10, dv dr, 4 pi r squared. We come up with our formula. We want to know the specific situation when the radius is 100. So sub in 100, and I've got minus, how many zeros have I got there? 1, 2, 3. So minus 400,000 pi, and the units on this one would be millimeters cubed per second. Spherical bubble, expanding. So this time we're blowing the bubble up. This time, when you're blowing a bubble up, or a balloon for that matter, I suppose, but imagine you've got one of those little bubble machines, you dip it in the soap, and go, and try and blow a big bubble. But of course now it's the volume that's a constant rate, because you just go, because if you change the volume, if you've ever blown bubbles, you know, if you change that volume, it bursts. You've got need a nice, even breath. So we want to know how that surface area is changing when the radius is 10 millimeters. So ds to t, I'll call it s for surface area. Alright, so what do we know? We know dv to t is 70. Now in this case, I'm going to need 3, because I want ds to t. I know dv to t. Now that means I need to link volume and surface area. I don't have a formula that links volume and surface area. So I'm going to link volume and the radius, but also link the surface area and the radius, and then we can create what we need. So there's the one we just did. Volume, we know dv dr is 4 pi r squared, so we can put that one in. But let's work out a surface area one. ds dr would end up being 8 pi r. So putting it all together, 70, 8 pi r, the reciprocal of dv dr, and we get 140 over the radius. So that's saying to me that the change in the surface area is inversely proportional to the radius. So the bigger the radius, the smaller the change in the surface area. And that's right. Imagine someone blowing up. I wish I had a balloon here because I could get the effect real easy. Because as people blow up the balloon, you know how they get bigger and bigger. And people start going, no, it's going to burst, it's going to burst, it's going to burst. And you put one more breath in it, but it only goes up a little bit. People go, ah! And everyone's on the edge until finally it bursts, of course. Okay, sub in 10, and we get 14 units for this one. We're talking about an area, aren't we? So millimetres squared per second. Now, of course, we now know integration. Last time we looked at rate of change, we'd only done differentiation. So we can go back the other way now as well. If they give us rates, so in this case they've given us dv dt, I could work out v in terms of t and things like that. So here's an actual HSC question from a couple of years ago. Again, they love these spherical things because we've got a formula for it, it makes life a bit easier. So a raindrop this time loses water through evaporation at a rate depends on its surface area, and the change in that volume minus 10 to the power of negative 4. What's that? 0.00. Hang on, try that again. 0.001, wouldn't it? Negative 4, yeah. Times whatever the area happens to be. Okay, we have to show that the rate of change of the radius is constant. The radius is constant. Okay. How do I do that one? So it's dr dt is what I'm trying to work out. And what have they given me? They've given me dv dt. Okay. So dv dt, I want something that links volume and radius together. I've got that. So we should be able to do this. So dv dr, again, once again, there it is. Dv dr is 4 pi r squared. So dv dr is in fact, and that's what I was talking about before, the surface area. That's the trick with this one. If I change that to be just a, then when I sub into our formula for dr dt, I get minus 10 to the power of negative 4a times 1 on a. The a's cancel and I get left with a constant number. So I guess the trick to that question was realising that 4 pi r squared was in fact the surface area. Either that, or I suppose if you didn't notice that, then you'd have on dr dt 1 over 4 pi r squared, but you could substitute in for the surface area 4 pi r squared, and again it would just drop out then. Okay, so that was the first part of the question. How long does it take for the raindrop, and its volume is 10 to the negative 6 metres cubed, and we want it to completely evaporate? We want that volume to go down to 0. Right. We now know dr dt is minus 10 to the negative 4. I also can work out what the radius is, because they've told me the volume, and I know the volume is 4/3 pi r cubed. It's not a neat little answer, but there it is. The cubed root of 3 times 10 to the negative 6 over 4 pi, whatever that works out to be, that would be the radius of our raindrop. Now I can use integration. Now when we integrate these sorts of things, we like to separate the variables. Everything with r on one side, everything with t on the other, and that includes the dr and the dt. And then I'm doing, what you do to one side of the equation, you do to the other. So I'm integrating both sides of the equation. Now, the limits, you put in the appropriate limit to the variable. So on the bottom of the on the bottom of the integral symbol, on the right hand side I'm saying when t is 0, on the left hand side, the radius is that wonderful number that we just worked out. The cube root of 3 times 10 to the negative 6 over 4 pi. On the top, I'm saying, well, t, that's what I'm trying to find, the term for it to evaporate. Well, when it evaporates, on the left-hand side, logically the radius would be 0 because it's not there anymore. So this is the equation I have to solve. Fortunately, the integration is quite easy because integral of dr is just r and integral of dt is just t. So I've swapped sides there, but 0 to t of t would just end up being t if you think about it. Because if you integrate the t, you'll get t, substitute in t, minus substitute in 0, So anytime you see that sort of thing, integral from 0 to whatever the pronumeral is, you can just go straight to t. I mean, you don't need to muck about there. That one's obvious. The other side's not as obvious, although the other limit is 0. Now notice I did something else though. See how the limits have swapped? And I've put 0 on the bottom, and the cube root of 3 times 10 to the negative 6 on 4 pi, I've put that on top. But what else have I done? Remember, you can always swap the limits, but you've got to change the sign. See, it's no longer negative. I've now made it positive. Okay, so sub in, and we get 10 to the power of 4 times the cube root. I think it's about time we approximated. It's starting to get a bit ridiculous. So around about 62, and the units is seconds for our raindrop to evaporate. Not a heck of a lot of questions, but remember, it's just a recap on rates of change from before. But now we can use integration as well as another tool for rates of change problems.